Good afternoon, everybody, and welcome to the Construct Innovate webinar series on digital construction technologies. My name is Jamie Goggins, and I'm co-director of Construct Innovate, which is Ireland's National Research Centre for Construction Technology and Innovation. This week in the webinar, we're going to concentrate on connected construction and the Internet of Things. This is part of a 6-week webinar series. So if you missed any of the previous weeks, then you can find them on the Construct Innovate YouTube channel or go onto the Construct Innovate website and you will find the recordings of the previous webinars on that. This webinar has been recorded and will be made available to people afterwards on the Construct Innovate YouTube channel. We've got 3 fantastic speakers this week again, very, very fortunate. So our first speaker will be Lala Rukh Memon, who's a graduate researcher in the MaREI Centre based at University of Galway. And she's going to talk about a new type of contract, which is called Energy Performance Contracts Plus, which should guarantee operational performance of buildings through contracts. Then we have Conor Redington, who's a researcher in Construct Innovate at University of Galway, and he's going to talk about using the Internet of Things to identify performance gaps in operation of dwellings, and in particular focus on the case study apartment block. Then we have Professor Sheil, who's director of the Cambridge Centre for Smart Infrastructure and Construction at the University of Cambridge, and he'll talk about smart infrastructure and construction. So each of our presenters will present first, then we'll follow by Q&A at the very end. So if any questions for any of our 3 presenters, please do pose them in the Q&A function at the bottom of the screen. So you can pose your questions as we go along. We'll pick them all up at the very end. So that's in the Q&A function at the bottom of the screen. So without further ado, I'm going to hand over to our first speaker being Lala Rukh Memon, who's a graduate researcher in the MaREI Centre at University of Galway, who will talk about Energy Performance Contracts Plus, which hopefully would guarantee operational performance of buildings through contracts. Over to you, Lala.
Thank you, Jamie. Can you see my screen?
Yes.
Okay. Yeah, hi everyone. This is Lala Rukh, and I'm going to present my PhD work on Energy Performance Contracts Plus assessment framework, and this guarantees the operational performance of buildings. So we're going to start with the introduction, and then going to give an importance of why EPC plus assessment framework is important, and then I'll explain on how we developed this framework, and then which follows by the real-time case studies from my PhD work, and then we look at the final EPC plus assessment report, how it would look like. So EPC is the energy performance contract. It's essentially a financing mechanism in which the energy upgrades are paid by the guaranteed savings they generate. So if you look at the graph on your left, in over the time, the cost of the energy, operational cost of the buildings would be very high if there are no works done. But in case of EPC, which guarantees the performance, there are these savings which we see in green. So over the time, the blue savings are paid off to the energy service companies, and after a certain years, based on the contract, it is then the benefit to the customer. So the benefit of these type of contract is that they legally bind the service company, and they penalize if there is no benefit coming to the homeowner. So homeowners essentially are then out free of any kind of risk. So the problem with this kind of framework as of now is that it only assess the success of the works done through the energy savings alone. But even in the energy savings or the CO2 emission saving, there is significant performance gap if you look at these just the if there is an audit once in a year or so. So there's this image that we are looking at this slide. It was a 5-year building performance evaluation study done in UK, and then we can clearly see there's at least like an average 3.5 times gap, but then the gap between the actual and expected performance goes up to 10 times. So in these kind of cases, EPC gives us an edge, and then there are other additional benefits which we can also measure. For example, there in a building, especially if you're talking about homes, there are important environmental and socioeconomic indicators. For example, we can monitor temperature, humidity, indoor CO2, and then of course mold conditions. So with the With the continuous monitoring, it's achievable, it's straightforward, and then also cost effective. So this new developed EPC plus assessment framework has environmental, social, and economic parameters, and then which are like sustainability at the center of these. When we originally envisioned this project, we were kind of hoping to like have an annual report card for each building, and this is now actually the whole system comes together, and based on our all the criteria grouped into three main criteria, we have a score for all the criteria for a certain building at the end of the year. So this is just a trailer of what's gonna come ahead. So we have developed this broader system for the project, and in which we have the physical layers, meaning we have buildings information, and then we have sensors installed in these buildings, and through a gateway we collect signals which come to our computers, and then we can use for our analysis and developing this assessment report as well. So starting our criteria, first of all, we are looking at the temperature criteria. So this is coming from one of the houses, which is house number 26, and we're looking at the data from September 2022 to June 2024. So what we're looking at, like we are recommending certain temperature ranges. For example, the recommended temperature range for this, like for all the houses, is 18 to 24. And now we're looking at the number of hours, how many hours in a year or in a month here, the data was within the ranges. So if it's within the ranges, we are looking at green bars, and then it's assigned a score based on that. So for example, let's take the example of March 2023. It has a 0.95 score, meaning it's 95% of the time it was within the allowed limit. So it's a good performance. But then if you look at these May 2023, it's 0.23, meaning only 23% of the like hours it was within the prescribed ranges, and like rest of the time it's out of. And then we can also see if it's below the limit, in that case it's the blue, and if it's above the limit, it's then like of course red. So like in May, June, we are seeing overheating problems in this particular home. The same kind of analysis is done for relative humidity, and the results don't look really good here. Humidity is always like not like in most of the cases it's above the limit. Like we see the red graph, and we really want to see that. And like given, especially in this condition, if we have high humidity and comfortable temperatures, this is very likely atmosphere for mold growth. And the same kind of analysis we do for CO2. So for CO2, we just, with there's no minimum range, of course, but then we're only looking to have it below 1000 ppm. So what we're looking at these exclamations, which is for the insufficient data. So in some of the cases, for example, if we don't have sufficient data, which is at least a 70%, to draw a conclusion or to assign a score, if we have any lesser data than that, then we just don't assign a score. We're not only looking at the averages and hours of the performance, we are looking at the of how in general, like remember I talked about if the humidity is more and that the temperature is even comfortable, it can be a mold related condition. So this is an other parameter which assigns a weighted score based on how our indoor environmental conditions are. So we're going to plot. We have plotted the data in this matrix of like 11 different zones. So ideally, we want our house indoor conditions to be within A1, A2, and A3, which have a positive scoring of 1.6 and 0.3. And we never want our house conditions to go in the region GHI, which is a region which is very prone to mold conditions. And then there are these other zones in this map as well, which has a 0 scoring. So for example, this is house number 26 again, the same house, and this is the plotted data from 2 years. So we see these are thousands of data points coming into this home, and then based on that, when we calculated the weighted score, this house has a performance of 0.586 on a scale of 0 to 1, so which is not a good performance. So we can see, even though like a lot of the time the conditions are in A1, A2, and A3 region, but like because of the negative scoring, when it goes to the region H and I, which is more prone to mold, it gets a negative scoring, and the overall score of this house is reduced. Moving on to those were our environmental, indoor, and outdoor criteria, and now we're looking at the socio-economic performance. So in terms of measuring the social and economic performance, we have the time of use parameter, then building energy ratings, solar performance. So some of our houses that we monitored have solar, so we look at how much we get from those, and then finally a behavioral readiness index. So the other sensor that we installed in these houses measures the electricity consumption over the time, and then not only just, and we are able to look at the how much the primary and total electricity these houses consume. And then in addition to these, the sensor also allows to look at monitor like circuit level um, consumption in different parts, which then will give us more opportunity to look into further behavioral kind of things. So the first parameter in terms of the socioeconomic assessment is our time of use scoring. So we know there are various electricity service providers in Ireland, and based on like averages in journal, how much the cost is for like what time zones are there. So like we have an average of 4 time zones based on Ireland's market, a peak time zone, daytime, nighttime, and off peak. So there is of course a negative or like scoring or lesser scoring for the peak time. So for example, which is the 5 p.m. to 7 p.m. And then there's a neutral scoring for daytime. There is a better scoring for nighttime consumption, because there is, of course, we are paying less for it, and then it's better for the grid as well. And then there is a very, very positive scoring for the off-peak hours, which is 2 a.m. to 4 a.m. and in some cases 5 a.m. So if we look at the performance of a house, which is house 36 from the year 2023 and 2024, we see, of course, this is like kind of expected results from a house. Like majority of its consumption in the daytime, but a good chunk is in the nighttime, and then like almost the same for the night peak time, peak hours, and there's a very slight consumption in the off peak hours. And like as overall the results are for like same for the 2022, 2023 and 2024, the score is 0.29 on a scale of 0.21 to 1. Moving on, so these are our parameters for the solar home. So we look at the self-sufficiency index and peak performance, peak period performance. So the self-sufficiency index, which is the green meter here, it tells us how much the house meets their own demand through the solar its installed PV. So it's, for example, in this case for the house number 1, for year 2022, which is only just 2 months of data, it's meeting about 17%. For 2023, it's slightly better and 15. And then there's another parameter which says peak window share, which meaning we're looking at how much the solar is meeting its demand during the peak hours. And this is another result from house number 54. Finally, another parameter is the behavioral readiness index. So SEAI recently published a very new report, which is the Behavioral Insights Electricity Demand, and they classifies behaviors into 6 different categories based on the 6 different categories: frequency, agent, behavioral effort, cognitive, financial cost, and energetic impact. So drawing from that, I have categorized my circuits into 3 main categories: low effort, medium effort, and high effort, and then assigned a score. So for example, for low effort, there's a score of 1, for medium effort, there's a score of 0.5, and for high effort changes in electricity behavior, there's a score of 0. And we're looking on the right, we're looking at the sample results. So for example, for house number, and then we have this behavioral readiness index score for overall time and also for the peak hours, because from this report, the peak hours are even more important, and we can begin to try our behavior, especially during the peak hours, because that's the most expensive part and that's most heavy on the grid as well. So for example, house number 11, if it has a score of 36%, it says it's 36% it's likely that the house can change their behavior and get better results. And but then the same house has 2% readiness index during the peak hours. And then, for example, for the house number 36, for which we have the overall report, this is the final score report card that I showed you earlier as a trailer. So this is report for house number 36. And I'm continuing like a kind of from the BRI score. It has a 0.17 17% score for the behavioral readiness index and a peak score of 0.22. So this is what we envisioned for the project, and it divided into three main criteria: criteria, environmental, indoor, outdoor, and socioeconomic. We have this performance. So we are looking at, for example, we discussed temperature. So it's now we on based on our scale, we can decide if this house passes or fails, because all of these scores are for the year 2023, and we can clearly see that in case of relative humidity, the overall score is even less than 70%. So this house clearly fails the expectations. Indoor CO2 kind of looks like okay, and then 0.81 for the temperature versus relative humidity, we pass it, and then so on. So that's pretty much it from my side.
Brilliant. Thanks, Lala. So really interesting, I suppose, methodology in terms of a performance contract that could be included in the initial contract between, say, a client and a contractor, or that's going to deliver this work, where you can guarantee performance, and then that scorecard at the end where you can set what the minimum score is going to be. So that all those criteria would be set in the contract, what those numbers are, whether it's 70% or 60% or 90% as well for each one of those in there. And there's loads of flexibility within that system. So if anyone has any comments or feedback for Lala on that proposed energy performance contract plus type contract, please do post them in the Q&A function at the bottom of the screen, and we'll deal with those after all three presenters. So we're going to move over to our second presenter now. Our second presenter is Conor Redington, who is going to talk about the use of Internet of Things to identify performance gaps in the operations of dwellings, and in particular focus on a case study apartment block. So over to you, Conor.
Thanks, Jamie. Okay. Okay. Yeah, thanks, Jamie. As Jamie mentioned, my name's Conor. I'm a PhD researcher here at the University of Galway, and I'm just going to walk through the work we're doing at the moment, or I'm doing, to look at the information we're getting from IoT sensors in an apartment block. The broad term is measurement and verification, or the broad use case for IoT devices in construction. And I'm just going to walk through then what the performance gap is for us, or in this research, and how we're approaching it and trying to diagnose it. So just seeing that it exists is one thing, and then trying to get a sense of what could be causing that gap is another. And I'm going to touch quickly on some of the research I'm doing where there's there can be mismatches between what the information you're getting and what you're hoping to measure. And for the following data, I'm trying to just showcase the methods that we're using. So none of these are conclusions being drawn, but just trying to give a sense of how we're approaching the problem. Just on measurement and verification, this is a broad term, can have a lot of positive benefits in terms of confirming that your design goals are being met. So you're putting in these sensors, you're getting a sense of how it's actually doing based on what you expect. And then, as I mentioned, identifying things like the performance gap, and hopefully pushing towards diagnosing why the gap exists. It can also be used for, as Lala's presentation showed, monitoring the indoor environment for human comfort and well-being, and along with that, meeting your reporting requirements. So using this data to back up your points in reports, or to just inform generally report making, and finally as part of iteration. So giving you information on the next project, or even on the way you deploy sensors based on what you want to know in the next one. So having this iterative feedback, the IoT devices can be very useful for that. These are the two sensors. So the apartments that we're looking at, there's 53 of them. They're in a set of apartment blocks, and each one has two of these sensors on the left and one on the right. So the one on the left is for indoor environmental quality. So you have your CO2, humidity, and temperature, and the one on the right is electricity consumption. From an IoT perspective, the one on the left is using LoRaWAN, and the one on the right is Wi-Fi. So it's just another factor in that kind of hierarchy, or the technology stack, is to think about the protocols being used. So LoRaWAN would be very low power. You can kind of put these devices anywhere, and the Wi-Fi is a bit easier to interact with. So as I mentioned, there's two of the one on the left per apartment for the living area and the main bedroom, and then there's just one per apartment. These are current transformers on the right that measure the currents, the circuits coming out of the main circuit board. So DEEP is an assessment procedure, and it's used for the BER, the Building Energy Rating. The BER initially functioned as kind of an asset rating. A couple of talks ago, Kira Hearn was on and talking about this, that it started as an asset rating, but it started to become a measure that we're using to find policy. And I've noted one big example here would be the Climate Action Plan. So this B2 rating for 500,000 homes by 2030. And so it's becoming a target, and just trying to, I guess it's always important to establish that we know what this target is, that the measure doesn't just become somewhat empty, and that it's representing reality. This is our measure of the performance gap. You could do it along a couple of dimensions. Here we're specifically looking at space heating. So you could have a performance gap between your expected temperature and what you're actually having, average temperature, or the lighting use and what your actual lighting use is. But here we're just concerned with space heating. And we have DEEP output, so that evaluation procedure output for the expected monthly water, ventilation, space heating use for each apartment. And then we also have that value from those various streams ongoing. So that's the data for a month. And the performance gap then is just a unitless number. That is the actual monthly energy usage minus the expectation over the expectation. So it's kind of in units of the expectation. Performance gap of 2 in absolute terms is that the actual energy use is twice, 2 times the expected, but in relative terms, it's 100% greater than the expected energy use. So that's just an important note. So here I'm showing a plot that we're trying to use, and I'm just going to break it down first, and then maybe go into it, just because I know maybe box plots aren't that intuitive. So on the right, I've just taken out June here, and I'm just showing what's underneath this box plot is that you have these data points. Each point is an apartment's performance gap. So on the y-axis, you have that unitless number, and you can see there's kind of a bundling of data points, and what the box plot can help to do is just tell you how saturated that bundling is. And the box itself represents 50% of the data. So you have 50% of the data lying in that interval that the box covers. The horizontal line then is the median, so it gives a sense of the expected value of all these apartments' performance gaps in that month. And then you have what are they called, whiskers, and they try to extend to 1.5 times the range, which is that the range is that middle 50% value, and 1.5 times is just an arbitrary value. You can change that, but by standard it's 1.5, and that's just to give a bounds on what you would expect. So anything outside that is considered what's called an outlier, and that's not really that too technical, but it's just a sense that this point is really far from what we'd expect. So the reason we're kind of looking across months like this is because often this number is summarized, this performance gap number will be summarized by a mean and one kind of point estimate value. And I think it's useful to try and if we're trying to understand the gap, to see that there's quite a bit of variation within months across devices, and then also across the year. You have seemingly going way above and sometimes going below. So that's why this profile offers a bit more than just a static number. And the another with newer homes, the deep estimate can tend to be a bit underestimate the expected use, and vice versa with older homes, it'll overestimate the expected use. So some of these values seem quite large, but once again, you kind of get a sense of that it could just be one or two devices really drawing out things, or it could be just that deep assumption that is causing that consistent gap. Um, okay, so this is another kind of busy slide, but I'm just showing how we're maybe trying to approach understanding. So you have this bigger plot, and you're trying to think about, okay, what could be common between some of these devices within this plot. And the way you might do that is to think about other piece of information you have. And for us, we have the deep information that's used in the initial calculation. On the bottom right, I'm just showing here for an apartment. If we looked at the total wall area and then the percentage of that total wall area that was exposed to the outdoor environment or external environment, and we looked at that ratio, would that have an impact on the general variability? A similar plot to this for a home. So each bucket here, so say in the middle top here, we have 0.3 to 0.41, and that's the ratio that I just mentioned there. So that's the ratio of the fully exposed to the outdoor environment of the wall area for that apartment. So each apartment in this, 11 of them, have that within this boundary of that ratio, and you're trying to see if there is a flattening or if there's a reduction in variation. So if you saw, for instance, on the bottom, you might see that there's maybe more of a straight line. The trend across the year disappears. You might try and think about that, or if the variation gets smaller within across devices, you would seemingly explain some of the performance gap from this factor. So you have a range of these factors with the deep information, and this is just trying to demonstrate that this is how we might look at it. And also just mentioning on that deep bias that I talked about before, that deep may possibly be consistently underestimating the expected use. What you might see is that no matter what factor you try and categorize by, this plot doesn't change. So that might hint at the fact that there's just a constant buffer, which in itself isn't always a problem, but it's important to try and understand what assumption is maybe causing that buffer to exist. So from my own work, I'm trying to understand the space heating system. So understanding the variability from maybe a more technical understanding of it. What's in these apartments is an exhaust air heat pump. So it works as a regular heat pump, but the air in is exhaust air, so from the bathroom or the kitchen. And we have that as one circuit called the air handling unit. You'll see that in a few slides. But then the way we understand the system is that there's also help from backup heaters. So it's kind of external to the heat pump that can bridge the gap of any if the heat pump can't on its own meet the temperature requirements, there's backup heaters that work for helping the heat pump, but also for domestic hot water. But we just see that as one heating circuit. So this is a similar kind of, you understand the physical system from one point, but you have a certain proxy of information. So that kind of the classic, the map and the territory. And this is some profiles of 4 apartments across 2 days, just to give a sense of how what this might look like in your head here, and then what you see from the IoT sensors and what the data you're collecting. And it's also just to show as well that we can look and combine. So previously I combined the deep information to try and understand variability, and here for those same 4 apartments, I'm trying to combine the temperature profile. So I've dotted the red line here is for 20 degrees. So seemingly, the target temperature you might want consistently. And just trying to use this as another tool to understand the apartments you're looking at. And especially one of the big factors is trying to broadly understand. So you have 53 apartments. You don't want to extrapolate too much from even 4 or 3 or 2. You always want to be keeping the variation in mind, because going back to that monthly plot, you could see within there's a lot of variation. So you don't have to be looking at the outlier and thinking it's the norm. So within our minds always is to try and uh, keep a broad view as possible without completely confusing ourselves. And that's also just shown here. I've shown the non-heating season for in June, and this just to show that you can kind of look at more apartments. So this is 12 apartments at once, and just getting a sense of their temperature profiles. You can see obviously the red line's gotten a lot lower because it's much hotter in the apartments. But it's just, again, trying to give a sense of how we're trying to keep the broad view in mind and not get too bogged down into any one particular apartment. Uh, to focus then, finally on benchmarks. So Lala showed some nice work of what she's doing with like metrics for understanding, are we meeting these requirements, specifically in the IEQ, in the humidity and temperature. Um, and at a broad level across the apartments, on the x-axis here, you have each apartment is a tick, and this is the percentage of hours out of all the hours of data we have on each apartment where that hourly mean temperature is above 25 degrees. And I've just put in a red line for an example of a benchmark. So the 10% there is the passive house kind of overheating standard. You don't want to be above 25 degrees for 10% of the year. And so I'm just trying to demonstrate and something we're using to just give a sense of benchmark combined with looking across and broad profiles. And you can see the temperature profiles are split between the two sensors. So you have the living area and the main bedroom. Similarly, this is for relative humidity. I've taken the hours where the mean value is within the range we want, which would be 30 to 50%, say, as a kind of crude estimate. And this shows just, yeah, that once again, the living in the main bedroom, but also just giving a broad profile of how all the apartments are looking at once, and kind of trying to maintain them in your head all at the one time, which is, yeah, a big part of not extrapolating too much from 1 or 2 data points. So just to sum up, um, sensor data is useful for testing a hypothesis, as I mentioned there, whether it's just combining information through the time series, having the temperature profile and the space heating profile, or it's looking at the deep factors and trying to break up a plot to see what factors are really influencing an aggregated measure. The IoT devices, really offer help there. Also on benchmarks. So I showed there you're broadly looking across and trying to see benchmarks and motivating further information. So I mentioned at the start about that iteration, that trying to understand what you're measuring versus what you're seeing. So when I talked about how I understand maybe the space heating system as having these backup heaters, but all I get is one kind of aggregated measure of heating. So that kind of method of, if I want to understand that at a finer level, maybe I need to think about that strategy of deployment of sensors. And broadly just find it really useful to create visuals to look across the apartment. So to not over extrapolate from 1 or 2 data points, really get a sense of what's going across broadly, consistently, can help in terms of just understanding the performance gap, how varied it is versus how not varied it might be. So having that broad profile has really helped there. So I'm hoping people found that interesting, and could apply it to their own space, from different stakeholders' perspectives. Thanks.
Brilliant. Thanks, Conor. So loads can done. I suppose you've just shown some examples there from the data. Once you get sensors in there, you can measure a lot. But you're trying to, I suppose, give a flavour of how you might analyze the data to help you make some informed decisions in there. But there's loads and loads you can do once you get some sensors, some data in there. So I'm sure there'll be plenty of questions for you on that. So without further ado, I'm going to move on to our third presenter. Third presenter is Professor Brian Sheil, who's Director of the Cambridge Centre for Smart Infrastructure and Construction. And he's going to give us a flavour of some of the work that they do there around smart infrastructure and construction. So over to you, Brian.
Thank you, Jamie. Hopefully this is coming through okay for you.
Yep.
Okay, great. Thank you. And so to motivate my talk, I'm going to show here a photo of Islington Tunnel in the UK. And I'm showing you this photo because recently I joined the Canal and River Trust on an inspection of this tunnel during a beautiful day over the summer. So this is a canal. It's quite an important part of the transport network in the Islington area. It's still in use. I just want to take you through the inspection process that we went on this day. So essentially, we hopped on a boat or a canal boat, and we were going to be taken through by the Canal and River Trust. We were given flashlights and a printout of the previous mandated principal inspection, which is some 39 pages of mainly text with at the end a map of the defects. And so as the boat was trundling through this tunnel, we had to use our torch to spot by eye and based on the map of the defects, which cracks and spalling were new, which ones have gotten worse, and which ones were safe to ignore. And we were focusing on one side of the tunnel. Once we got to the end, the boat turned around, we started to move back through the tunnel. I started to notice that on the way back through, the boat was going faster because the driver was starting to get hungry. And then as we got to the end of the tunnel, now I was starting to get hungry. And so I'm starting to think, is that crack really a crack? Who cares anymore? And so essentially, this is how we undertook a principal inspection for this tunnel. This is not an isolated asset. In fact, this is how we manage the vast majority of our critical infrastructure across the UK and indeed Ireland. Network Rail did their own internal study, and they showed that when two inspectors walk the exact same tunnel, maybe a day apart, they will agree 40% of the time. 40%. They even joke with us that some of their tunnels are self-healing because when they go back to the tunnel, they can no longer find the defects that they found in a previous report. So there's a few things that became apparent. First of all, this tunnel is old. In the UK, we very much have a Victorian masterpiece. This one in particular is over 200 years old and it's deteriorating. And when I mean deteriorating, I mean visibly you can see bricks falling from the wall. Now, the asset owners have a very real decision to make on whether to close at an enormous expense this canal that's very much in use to undertake essential repairs, or to run the risk of further accelerated deterioration and higher risk of ultimate collapse. And they are personally liable for a collapse scenario. The problem is the way we inspect that process is exactly as I've described. It's manual, and the reporting process is manual. And this, combined with the fact that degradation is non-linear, this is not a problem that's going to go away. In fact, it's going to get a lot worse. When you combine these non-linear degradations or this accelerated degradation with entirely manual processes, our existing processes and systems can't really cope to meet with that demand. And so Network Rail are falling further and further behind in their mandated principal inspections, and they're getting fined by the regulator. So with this short talk, I want to convince you of three things. First of all, I want to convince you that this combination of degrading assets and manual processes is driving a real demand for digital solutions. Now, I'm using existing infrastructure just to illustrate my point, but this same argument applies to new infrastructure where we have higher and higher quality assurance requirements, such as, for example, Grenfell Tower and fire stopping regulations, or indeed in new nuclear. The second process is that there's a very exciting way forward where we can combine LiDAR scan data with AI in order to be able to undertake digital inspections. But the third point I want to convince you of is that we're not quite there yet. And the main reason we're not quite there is because we lack data in the infrastructure or civil engineering domain. Now, there's a really important way that we can alleviate that, and it's what we bring to this conversation, which is civil engineering physics. And I'm going to show you in my talk, hopefully, how we can compensate for the lack of data by integrating fundamental physics into the process. So the opportunity here is we're now starting to get unprecedented access to data. And it's multimodal data, quite wide-ranging. The two that we focus on are for the visible LiDAR scan data. which is shown here in the left-hand side. This is a point cloud that you're looking at taken from a laser scanner. And from the invisible, we work a lot with ground penetrating radar, where essentially we have recast the ground penetrating radar as now an electromagnetic camera by building in the physics. And essentially we have now an ability to take photos of the subsurface just by recovering the physics of what you're seeing in the diagram here. Given time, I'm going to focus on our work on LiDAR data. And essentially the mission we have been on at Cambridge is to develop automated methods to, in the first instance, to be able to understand what we're looking at in this data and to be able to focus in on the structural elements that we really care about. For the here and now, to be able to detect problems as soon as possible, but also to be able to inform better. Now, better might mean more sustainable, more efficient, safer, and so on, both designs and processes. So our vision is for digital inspector, for infrastructure, for aging infrastructure. Our target is, in the end, to be able to safely extend the life of that asset. For new infrastructure, we want to, of course, ensure high quality construction on the fly, and ultimately to optimize productivity. Given all of these processes are manual, there is a significant productivity gains that we can obtain by introducing digital tools. We need to include systems thinking in our approach here. So all of the decisions typically for this infrastructure system is made at a network level. So if you think about budget management, resource allocation, risks, and so on, that is done at a system or network level, but requires detailed information at a lower asset level. So things that we're interested at the asset level is, digital recovery of defects, how we prioritize those defects, and how we undertake risk. And essentially what we're looking for is the outcomes we seek to realize is from the system, and all new construction projects are an intervention on the system rather than an isolated project. So naturally, when I talk about this, the first answer I get is AI is going to come to save the day so we can kick that can down the road. And unfortunately, it's not that simple, because indeed AI brings a lot of promise, but also brings a lot of problems that we need to face. And the first being something I alluded to earlier, which is a lack of data. And so a lot of the very powerful AI algorithms, and specifically now I'm starting to talk about deep learning, are supervised. And that's the brand of learning that we pursue. And what I mean by supervised is we need a lot of data where we have given the answer to these algorithms. And we simply don't have that data in the infrastructure domain. We think we do. So we think we have hard drives full of data, but I'm telling you now, we've got nowhere near enough data to train these really powerful algorithms. If you think about ChatGPT, it's trained on trillions of tokens. All of that then requires painstaking manual labeling. I'm fortunate that I've got my poor PhD students to that labeling, but that's not a very scalable approach. And ultimately, what we're competing against here is not other entities or other research groups. Actually, it's trust. So the models need a very high degree of accuracy. They need a very high degree of interpretability. As soon as somebody second guesses prediction output from AI and sends a person into the tunnel just to check, then it's game over. We may as well forget about it. So what we need is a very high level of trust. So I alluded to how physics can compensate data, and our view is that there's a spectrum. We don't need to pursue the extrema here of the traditional and the data-driven. And on the left-hand side, or the extreme spectrum on the left, is the conventional AI approaches that I mentioned, which indeed have quite large requirements for data. But just because we have now quite powerful algorithms, and just because we're starting to obtain data, doesn't mean we should abandon over a century of structural and geotechnical physics. And so on the right-hand side, we have those physics give us a lot of prior knowledge that we can build into the data-driven algorithms. It can give us a lot of interpretability and trust. And so we pursue this gray region here in the middle, where we can leverage the relative benefits of both sides. So we can start to adopt these very powerful algorithms, but build in physics to introduce prior knowledge and have some degree of interpretability and trust. And we encode that with prior knowledge, which increases that reliability, alleviates the big data needs that I mentioned. There are many ways to do this. Just one simple example that I'm going to show you of how one can do that is what we call pre-training. So I want you to imagine we have a powerful deep learning algorithm, which I'm showing here on the right, that one wants to train. And this is a first stage. So we undertake what's called a pre-training, where we've got a data set one, which is a large physics encoded synthetic data. So actually, this is the data set we are going to create ourselves. Because we're civil engineers, we know a lot of the physics in this tunnel. We can create our own data set that is entirely synthetic. And the analogy I use here is this is a bit like general education for this deep learning model. It's like going to school. It captures the general knowledge. It doesn't capture everything, but it captures the vast majority of the basics that we would need to know. And then we take that deep learning algorithm and we run it through a second stage, what we call fine-tuning in the AI domains. But essentially, we've got now a small amount of real data where we will fine-tune that deep learning algorithm. And the analogy here now, this is a bit more like on-the-job training, where it attempts to adapt that general knowledge to a more specific task. So this is an example of the LiDAR data that I mentioned. What you're looking at here, it looks like a model. It's not. These are actually individual points, and it's some 800 million individual points, in fact, in 3D space. So it's a very, very rich data source, but I would argue that it's very tricky to get information from this, actionable information. So I've seen engineers quite literally clicking off individual points to recover something as basic as the tunnel radius or diameter. For a machine to be able to do this, it's even more complicated because all the machine gets is a list of unordered points in 3D space. So in order to create that data set, one, we build our own physics-informed LiDAR simulator. And so essentially the concept here is with that data set one, we're going to do a lot of the grunt work. We don't need to capture everything because we're going to fine-tune on the real data, but we're essentially going to teach this deep learning model the vast majority of the physics that we're aware of. Now, this isn't just limited to tunnels, but I'm using a tunnel as an example use case. So this is all end-to-end parameterized by Python that calls a structural finite element model with realistic material modeling, for example, crack propagation, based on then the defects and the deformed geometry from that structural model after the calculation, that is automatically imported into a graphics engine. In particular, we use Blender, and that allows us to simulate some of these high fidelity graphics like pipelines and the walkway. Importantly, there is an entire separate area of research that works on the optics of this. And in the middle of this little tunnel here, you can see a little LiDAR simulator. So this is also a synthetic simulator that can simulate the optics of a LiDAR scan, where we can recover an entirely synthetic point cloud data set. And the kicker here is that automatically all of those points get labeled with the various components of the tunnel, with all of their defects and so on. Now, instead of dealing with the 3 or 4 real tunnels that I have on my hard drive, I can generate 10, 20, 30,000 tunnels that capture the basics of the physics that we expect, but doesn't capture everything, nor do we need it to. This is about being efficient in training so that we need a lot less real data for that fine-tuning stage. So this, in the end, is how our synthetic compares to the real data. Like I said, it doesn't capture everything we don't need it to, but does a pretty good job. And so one of the first steps we want to be able to do with this now, it's called segmentation. This is a very popular task in the likes of autonomous car space or in robotics. And essentially is trying to understand or give perception to the scene that we've been given. So here, what we're trying to do is identify in this scene, what are the components we really care about? So I've labeled these all in different colors, yellow being elements that we don't really want to understand or to analyze. All the other colors are coding the different segment types, the structural segments in that tunnel. We feed that raw data through a deep learning model. This is our own, so we've had to build our own deep learning models because off-the-shelf models don't work, which we call lining net. And that gives us a live prediction, click of a button. And so you can see here the accuracy by pre-training is quite good. So this is over 95% accuracy. So now we're starting to see or to be able to identify the components in the scene. Now, this is not the end in and of itself. This is a step towards further downstream analysis. So Now that we've been able to separate out what are we actually looking at in this complex scene, the next step would be to recover, for example, deformations. In fact, these are actually new tunnels where they did a scan immediately after construction and they wanted to identify the as-built quality. We partnered with collaboration with Hongxi, where they've got a lot of data from their metro systems. And you can see here the deformation patterns are quite interesting. They're strongly linked to how the tunnel is actually constructed and the ring pattern. The thing that we're very interested in is not just the deformation scan to scan, but also now understanding the deformations of the individual segments and how those segments are articulating relative to each other, because we want to understand how the segments are opening up gaps and joints, because leakage is actually a big design concern. So we're very interested in not just the global deformations, but actually the movements of those individual segments, which we can recover now quite easily. And the last step then is recovering defects. And this is for both new and existing infrastructure. So from a single LiDAR scan, essentially we're doing two things. One is we're taking virtual images, so we can simulate camera optics within that LiDAR scan to recover an image. And essentially the question we're asking in that image is, does this scene contain something that looks anomalous? And then from the 3D geometry, we're asking the question, which is this consistent with a normal deformed geometry, or is it consistent with a mode of failure? And then based on those two views, the 3D geometry and the anomalous 2D image, we are able to identify defects, classify them into their different types of defects, and also measure them so that we can rank their severity. And in the end, this is a prediction of some of these defects. So this is one of the virtual images we've taken, the raw image on the left-hand side here, where the light regions are showing spalling or brick damage. And the right-hand side here are the model predictions. The little number 1 here is the class, so it's predicting spalling, and the right-hand side here is confidence. So we're getting that interpretability as well, where we're getting low confidence rightly, where the spalling is a little bit more subtle. So we've packaged this up into a platform. When we spun out a company, this is being trialed across the UK now with National Highways Network Rail Transport for London, not just on tunnels, but also bridges. All of their data sits on the cloud. So we provide a nice 3D reconstruction of the asset and the ability to comb the data. So we run the algorithms to superimpose all the different types of defects. And here we're showing spalling, but also mortar loss or defects in between the bricks. We can also add additional features like construction joints and so on. We can set the severity thresholds according to the internal criteria of the company as well. And then at the very end, we can automatically generate the report. And I think this is the nice result, whereby now that we're using LiDAR, we're getting to scale millimeter precision outputs of those defects rather than a little bit more subjective visual examinations. Okay, so to close, I hope I've convinced you of the three things that I promised, that the aging infrastructure, acceleration, deterioration, and these manual processes are driving a significant demand for a digital revolution. And we see the digital inspector for infrastructure using physics encoded AI and LiDAR, providing massive opportunities. And what we as civil engineers have to contribute in this space is that actually there's significant pain points around data and data scarcity. But there's a lot we can do that leads to really interesting research questions around how we integrate our known physics to alleviate those requirements for data. Thank you for your attention.
Brilliant, Brian. That's very exciting work, and it's great to see things moving through I suppose, from a research desk to testing in the real world to actually then providing a platform to asset owners that are actually using it in there. So fantastic, fantastic application and huge potential as well for it. So if anyone's any questions for Brian or any of our other two speakers, then please post them in the Q&A function at the bottom of the screen, and we'll move over to that.